And so today we're going to continue this problem, and I want you to step back before we dive into the numbers and just intuition. Try to work on your chemical intuition. If you see this system set up and it's going to come to thermal equilibrium, look at A. A are the reactants. I only have 3 options, and all 3 options are at different energies. So most of my molecules are going to be in the ground state, a certain number in the excited state, the first excited state, and fewer in the third state. That's the Boltzmann distribution. You should be comfortable with that. Then the products, now we have degeneracy in the excited states. And so just statistically, there's more chairs there. Okay, if we're playing musical chairs and we throw the molecules in there, there are going to be more molecules in the excited state than there would be in the reactants. So the products are going to be more excited. So what do you think the sign is going to be on delta U, the change in energy? Or just think about this. Look at B. If I have more molecules in the excited state, will that energy be higher than in A? Yeah, because molecules are going to be in the higher states just because there's statistically more places for them. Okay, so energy is going to go up. So this should be what we call endergonic. It should go uphill. Ergs is another unit of energy. Okay, and so instead of endothermic, it may also be endothermic, but it's certainly endergonic. It's uphill in energy. Okay, going from reactants to products. What about the entropy on the left or the right? Which is going to have the higher entropy? The right. Remember, entropy is a measure of the number of levels populated. We have way more levels on the right, and so entropy should increase. Okay. So if entropy increases, then that if we look at the equations for delta G and delta U, when multiplied by temperature and there's a negative sign, it's going to make things more spontaneous to go to the right. And so it's possible that this would be a spontaneous reaction going to the right, but we couldn't really judge that definitively without doing the numbers. We would actually have to see if there was enough entropy change to overcome the positive change in energy. So it's uphill energy-wise, but it's got a higher entropy, so that's kind of making it downhill. And that's the competition for spontaneity. Is the entropy increase enough to overcome the uphill energy? And so that's what we'll do the calculations to see. All right, let's make it. So we have our partition functions. We have the probabilities, the 2 columns for our probabilities. Now to solve the internal energy, we just take the energy of each level and multiply by the probabilities and sum those. Okay. So we can do some of this work on the board, and then we'll just write the numbers in. So I'm going to rely on you to give me some of the probabilities. So for A, we have the ground state energy, 0 wave numbers, times the ground state, let's see, U is equal to this sum. So we have 0 energy multiplied by 0.5. Can I just do everything in 2 significant figures? It'll save us some time. So 0.5 probability. So that's P0, E0. The next one is 100 wave numbers. And what's the probability for that one?
0.31.
0.31. And then the last one, 0.19. So if someone could add that up for me. One more time.
Is it 69? Is it 69?
Yeah, 69 wave numbers. Excellent. Okay, so we can go put that in. Oh, there we go. So we have here 69. And it's the same kind of calculation for the products. And our degeneracies are already put in there in our probabilities. And so again, it's just the probability times those different numbers. So we'll go back. I'll do this one in table format. How about that? It'll be easier to see. So in terms of wave numbers, we have 0, 100, and 200. And then our probabilities were 21%, 0.21, 0.39, and 0.40. So we have 0, we have 39,
And 80.
and 80. So that's not bad. That's a faster way to calculate it. So 119. And now what's products minus reactants? So 119 minus 69. 50? Okay, so down here we have 50 for our delta U. And notice it's positive. So our intuition was correct. It went uphill in terms of energy. Internal energy was endergonic. It went uphill. Okay. All right, let's do entropy. So we have U over T plus in our lim Q. So for A, we had 50 or 69 wave numbers and 298 Kelvin. Here we're gonna calculate this for 1 mole. And we have the gas constant, 8.314 joules per mole Kelvin. Oh, let's see. We're going to not want to use this because our units are incompatible. So what are we going to use instead of the gas constant? What units are compatible with wave numbers per Kelvin?
0.69.
Yeah, the 0.695. Okay. So we're really not working in per mole, we're working in 1 particle. So this may have been your question, Jared. So we'll say 1 particle, and we'll use 0.695 wave numbers per Kelvin so that they're compatible. And then the natural log of our partition function. Is that coming across? Yes. So our partition function for A is 1.997, roughly 2. So that's it for entropy. Probably the most involved, and you've got to make sure that your units are going to be compatible. So instead of using R in this case, we'll use K because it's compatible with the units of our energy system.
So if you ask us if it's a 1 mole stuff or something like
Yeah,
that?
so if our energy was in joules per mole, then you would use the gas constant. Okay, so if our energy level system was separated by, say, 2,000 kilojoules or 200 kilojoules, then you'd be dealing with joules, and so then you would use the gas constant R. Who's finished this one?
I got 0.712.
0.712, so we'll just say 0.71. And it should be some sort of energy unit divided by temperature unit. And so this is correct.
I have a question. question about,
Yes.
so will you tell us if it's more than one particle, or do we always assume one?
In this situation, we're really just assuming it's one particle. So that you can, and that's one thing I'm going to point out on this little checklist for your written out answers. So we'll discuss that in a second. Yeah, that's a good question. So this is our entropy for system A. And what we'll see is that the entropy numbers are always about 2 to 3 orders of magnitude smaller than the energy numbers. Think about that. Why would that be? The entropy numbers are about 2 or 3 orders of magnitude smaller than the energy numbers. It's the energy divided by the temperature. Okay, and so we're at 200 Kelvin, and so we're shrinking that energy, and it's just a small amount of entropy. Okay, but it has a huge effect because later on, if we look at the equations, entropy is always multiplied by temperature. So it comes back up to being on about the same magnitude as energy or enthalpy. So entropy is a small effect, but it's always multiplied by the temperature. And so then it has a large magnitude. But this is a place where people mess up. You might have your energies listed in a table in kilojoules, but you look up the table for entropy and it's in joules. So there's a power of 3 there that's different. And a lot of times people will mess up their equations by writing their entropies in kilojoules when their energies are in kilojoules. Well, you've expanded the effect of entropy by 1,000. And that's a place where people mess up the calculations. And this will become clear as we do more calculations later in the semester. It's really a second part of the course point. But I just wanted to make that point here that if you're looking at 0.71 and the other number was 69, you're like, is that right? Yes. Yes, that's right. You should be comfortable that the entropies are really small. Okay. Can someone just quickly do the entropy calculation for B?
Just 1.48.
1.48, thanks. 1.48. Okay. So it's about twice as much. Okay. And so then let's do delta S. So products minus reactants. We just about 0.777. Okay, so that's delta S. So now let's move on to enthalpy. And so we look at the equations for enthalpy. It's U plus nRT. Okay. And in this case, nRT is really going to be KT because we're going to use that 0.695 wave numbers per Kelvin. Okay. H is equal to 69 wave numbers plus 0.695 wave numbers per Kelvin times 298. Let me emphasize yet again, you always use absolute temperature in all your thermodynamic calculations. So, what did we get?
276.11.
Okay, we'll just round to there. 276.
So ignore the decimals for temperature always, or?
We're just estimating. We're rounding all over the place, and so yeah, you can put the 0.15 in there if you wanted. But yeah, if you're doing this for lab, then in Excel and all that, use all of the decimal places and be as accurate as possible. But for an exam, when time is an issue, if you do the calculation right and you're to 2 significant figures, and I see that you know what you're doing, absolutely full credit, right? Because what have you done? You've given me a really good estimate, and you've shown me that you know what you're doing. That's what I'm looking for. I'm not looking for the answer to 5 decimal places or 5 significant figures. If you can do it to 2 significant figures, I know you can do it to 5. So I'm looking to see if you know what you're doing, and not so much that you get the right answer to a certain precision, right? Good. Okay, so this was 276. And that's important for you to ask that question because you got to know what I'm expecting. Can someone do that one for B?
326.
26?
326.
Oh, 326. I was like, wow, that sounds low. 326.
I think the delta that you use delta H is this.
Yeah, yeah. Sometimes it's
That's
that way.
crazy.
Yeah, yeah. And so then
Is that just coincidence?
it's
I think it's close because when I work on other problems,
it's not always the same.
Yeah, I didn't think so.
Yeah.
I was like,
So
is that what I'm-
it turns out to be 50 also.
Yes.
Okay, so it's both endergonic and endothermic, right? So the therm word we use for delta H is heat of reaction. We'll find out more about that in the second half of the course when we talk about sort of traditional thermochemistry. But we use therm to talk about heat in and heat out. And so endothermic is uphill in terms of heat. It takes in heat to go forward, and it's also exothermic. It releases heat. So now let's do A. So Helmholtz Free Energy. So this is when we first get a measure of whether it's a spontaneous reaction or not. So again, for system A, Helmholtz, this is system A. And the equation for Helmholtz energy is U minus Ts. And was it 0.71?
Yes.
So the units, I want to see units in all of your intermediate calculations. So even though you can just write 298 and 0.71, I want you to do this. I want you to show me how the units cancel. Okay. One, it shows me that you're being meticulous, and two, if I require that, you're going to catch a lot of your own mistakes. Okay. This would catch the mistakes of using joules and wave numbers in the same problem. If you didn't use your units, you can just throw the numbers in there and you're going to be way off. You're not going to know why. So I want to see your units. That's one of the things I'm checking in terms of a good answer. So someone tell me what this is.
-1, 2.
Negative 1,
142.
142. What?
For the Helmholtz, is it sort of like the Gibbs Free Energy where if it's negative, you say it's not?
Exactly. So this is spontaneous. So we can answer questions about this. You could look at that and go, spontaneous.
It says it was just like Gibbs, but with a different set of conditions.
So yes, it's for fixed volume systems.
Yeah.
So if A and B were in a fixed volume, and this reaction was taking place, it would be spontaneous in a fixed volume. So pressure could go up in that container, but it's a fixed volume. So it would be spontaneous even if the pressure changed in a fixed volume. So this is the Helmholtz Free Energy, so minus 112. And can someone do the other one? Oh, wait, no. This is the Helmholtz energy. We haven't gotten to the spontaneous yet. That's delta A. Okay, so, oh boy, let me go back. All these buttons. But I want to make sure this is a good video. So we'll go back to the video, Control 5, and then here we go. So I'm going to get the red mark and say, not yet. So not yet, cowboy. This is just A, not delta A. Okay. So, all right. So let's go back and write that in. So this was minus 142. Can someone calculate B real quickly?
Negative 322.
Negative 322.
So I think it's still going to be.
Yes. And so negative 322 minus negative 142. So don't screw up your negatives.
Negative 180.
Okay, negative 180. Now it's spontaneous. Yes, spontaneous, right there. It looks like spontaneous. All right, so that's fantastic. Let's now do G. These are obviously slower because I'm flipping back and forth between the board and so on. But once you get past the partition function and the entropy, the rest of the calculations are fairly quick. So this is H minus TS. So 50 wave numbers. Is that right?
Are you doing delta G or?
Just G for system B for the products. What is the H? What's the enthalpy for that? Oh, the enthalpy was, yeah, okay. What was it?
326 would be.
Okay, 326. And then 1.48?
Yes.
It's 276 for A.
This is B.
Are you doing
Oh, I'm doing B. Okay, sorry. I just, in my head, I've got all these numbers. Okay, so for system A, the enthalpy.
It's 276.
276, thank you. And then you get a sticker for catching my error and saying something. Okay, and then the entropy for...
I was going with you. I thought you could be first.
Okay. We'll get 2 stickers. They're cheap. All right, give me the entropy for system B.
0.71.
Point
For A, it's 0.71.
first. A, 0.71. Okay. Now we're good. All right, so I feel like I'm rushing. So if someone would evaluate that for me.
I got 64.
64 wave numbers. Okay. Okay, and then the G for B, the one I kept trying to calculate.
Negative 115.
Negative 115. So 64 and negative 115. So go ahead and take negative 115 and subtract 64 to get the delta G.
I got negative 179.
Negative 179, very close.
Close to 1.
Yeah. And again, because the internal energy and the enthalpy worked out to be the same, you see that that's the only difference between A and G over here. And so, yay, they're both spontaneous.
Will
We
they
also-
always be both spontaneous or not both spontaneous?
Depends on-
I don't know. I've never seen an example where one's spontaneous and the other's not. You know, but
But
with
it
the
could
constant pressure and constant volume, I guess it could happen. Yeah. So this is it. Now we could take that equation down at the bottom. Delta G equals minus KT in this case, natural log of the equilibrium constant, and invert that and solve for the equilibrium constant in terms of delta G and put that in. Or for the equilibrium constant, we could just take the ratio of the partition functions, and we showed that last time. So I think ratio of partition functions is a lot faster. And so you can just use your partition functions to calculate your equilibrium constants. So that's USHAG and K for this 2-level system. And it's fantastic. I love it. Okay, this is one of my most exciting parts. So this is the top of the mountain for this part of the course. Is going from quantized levels up to all the thermodynamic properties that you're familiar with, that we've been talking about from freshman chemistry, organic chemistry, whether reactions are spontaneous or not. These things depend upon entropy, which depends upon the ability to populate energy levels. And so this is the quantum roots of thermodynamics. So we're at the top of the mountain for this part of the course. So I'd like for you to pause. And if you don't pause at the top of the mountain and look around, you kind of miss the point. And so I want to give you note cards. If we take the test and I ask you to look around afterwards, no, you're already headed down the hill to the next trail. This is the point when you really need to stop and look around and think, what do I see now that's different about the world? When you get to the top of the hill, you look around at all the familiar things, but you see them from a different height. And so I'm giving you a note card. We're going to spend 2 minutes just to reflect on what you see differently now about chemistry and the world around you after having gone through the quantum roots of thermodynamics. And then after that, we'll get back to the practical side of things of what I'm expecting on the test. Okay, so we'll just do a 2-minute write. And I want the note cards back. You can, these, I don't guess there's any reason for this to be anonymous. I'd like to know what your thoughts are. So you put your name on there. This is not for a grade. It's just really to enhance your education by saying, wait, after I've learned something new, let's pause. What does this mean for me in my life? I'd like to hold you to 2 minutes, though, because this could go long. And so we've got 2 minutes.